Now that we have an algorithm for implementing Gaussian elimination, uh, we have what we need to talk about the complexity of the algorithm or how long it's going to take to execute. So we're going to do this using the standard computer science approach where we count the number of arithmetic operations and we use this to come up with a formula for the number of operations it takes to execute the algorithm for an input of size n. In other words, for an n by n system of linear equations. Now, before we do that, I want to work out some of the dimensions of the problem that we're going to need as we go along. So suppose we're processing the jth column so that all of the spaces below the main diagonal to the left of that column have already been set equal to 0. Now first we need to know the number of rows that we're going to have to process. Now we won't need to make any changes to the jth row itself, so we're only going to have to update the n minus j rows below it. Now going in the other direction, we're going to need to know the number of columns that we have to update when we execute each of the row operations. Now in this case, we do need to update the values in the jth column, along with everything to the right of that position. So since there are j minus 1 columns to the left, and a total of n plus 1 columns, this means that we're going to have to process a total of n minus j plus 2 columns to execute each of the individual row operations. Okay, with that information in hand, let's take a look at the algorithm itself. So first, let's look at the elimination part of the algorithm, starting with what's going on in the innermost for loop. Okay, first notice that this loop is going to execute a total of n minus j times. Since the division that calculates the multiplier will execute once per loop, that adds a total of n minus j divisions to the process. Now think about the row operation line. There's a lot of calculations condensed into that one expression. First, every element in the affected columns has to be multiplied by the multiplier. Since there are n minus j plus 2 columns to be processed, that means we'll need n minus j plus 2 multiplications, and then an additional n minus j plus 2 subtractions to get the new values for all the elements in the jth row. Now, those are the values for a single pass through the for loop. Since the for loop will execute a total of n minus j times, that means that we'll have a total of n minus j times n minus j plus 2 multiplications and the same number of subtractions for each complete execution of the for loop. So to get the total number of operations for the entire piece of the algorithm here, we have to add up these three expressions over all of the values of j, which according to the outer loop go from 1 to n minus 1. Okay, so now what we need to do is we need to simplify this expression to get an expression for the total number of operations that is just a formula in terms of n without the summation part. So there's nothing really complicated to this part of the process. It's just going to involve a lot of algebra manipulations. So on the left side here, I've got some useful summation formulas that we're going to need as we go along here. And on the top row, I've got the expression we ended up with on the last slide. So what I'm going to do first is I'm going to factor out the n minus j that all three of the terms in there have in common. So this becomes the sum of n minus j times 1 plus n minus j plus 2 plus n minus j plus 2. Okay, now I'm just going to simplify everything that's inside the parentheses, the right-hand parentheses. That expression becomes 2n minus 2j plus 4. Of course, still the n minus j out in front there. Okay, now I'm going to do two things. First, I'm going to factor a 2 out of that second parentheses. That's where the 2 out in front comes from. And then I'm going to multiply the whole thing out. Right? This becomes n squared minus 2nj plus 2n plus j squared minus 2j. Now, key thing to notice here is that j is the summing variable, right? N is a constant. N is the size of the system of linear equations, and we know that up front. So what I'm going to do is I'm going to rearrange this into three parts. The parts that don't have a j, that's the n squared and the 2n. The parts that just have a j to the first power, That's that minus 2n plus 2 times the sum of the j's. And finally, the j squared part, which is just over there by itself. Okay, now I'm ready to use those formulas that I have over there on the left-hand side. Remember, again, n squared plus 2n is a constant with respect to j. So I'm going to simplify that using the first formula, and it becomes n squared plus 2n times n minus 1. The middle part becomes minus 2n plus 2, and what I want you to think, you're substituting n minus 1 into the formula for m. So that becomes n minus 1 times n minus 1 plus 1, which of course is just m. And then I did the same thing again with the third term, right? I substituted n minus 1 for m plus 1, and 2m plus 1, and got that expression there for the third sum. Okay, so now I've really accomplished what I want, right? I've gotten rid of all of the summations. I have a formula in terms of n. All that's left is some really messy algebra, multiplying and combining like terms. And if I do that, we end up with this formula. 2n cubed over 3 plus n squared minus 5n over 3. That's the number of arithmetic operations required to execute the elimination part of our algorithm for an n by n system of linear equations. Okay, so how about the backwards substitution part? The real action is going on inside the for loop where we've got that summation part. So if we look at this section, we have to do n minus I plus 1 minus 1 additions for the sigma part. Remember, there's going to be one less addition than there are multiplications there, right? Because we add in pairs. Then we're going to have to add one more. That's actually the subtraction in the numerator. So that gives us a total of n minus 1 addition slash subtraction operations. Now for multiplications, we have to do n minus I plus 1 for the summation part. And then we're going to have to add 1 there too. That represents the division by the a sub I term, which gives us a total of n minus I plus 1 multiplication slash divisions. So what we need to do is we need to add all of those up as I goes from 1 to n minus 1. The loop goes the other way, but we'll do them in the proper order here for the sum. Plus 1. That plus 1 is for the calculation of the x sub n all the way at the top of this section. Okay, so again, we're going to have to do some algebra manipulations here and then ultimately use those same summation formulas again. So to start with, I'm just going to simplify what's inside the parentheses. That comes to 2n minus 2j plus 1. Then I'm going to do the same split here. I'm going to split this into the parts that have a j and the parts that don't have a j. Because the parts that don't have a j, the 2n plus 1 there, that's essentially a constant, right, with respect to that index variable. So the first summation becomes 2n plus 1 times n minus 1. That was the first formula from the previous slide. And the second summation becomes n times n minus 1 over 2. Again, with that 2 out in front. Okay, now again, it's just algebra, right? If I multiply out the parentheses, if I cancel the 2's, multiply that part out and distribute the minus sign, it turns into this, 1 plus 2n squared minus n minus 1 minus n squared plus n. And that simplifies quite nicely down to just n squared. Now, this is all the information that we need to get to our final answer. I'm going to add those two expressions together. The 2n cubed over 3 plus n squared minus 5n over 3. That's from the elimination phase. N squared is from the back substitution phase. We add those together, we get this 2n cubed over 3 plus 2n squared minus 5n over 3. And again, we're using the computer science approach here. The lower order terms are dominated by the higher term. So ultimately, my conclusion here is that our algorithm is going to run in big O of n cubed time. So if you've taken an algorithms class, say in a computer science program, you know that big O of n cubed is not great. It's not horrid, but it's not great either. So ultimately, kind of the takeaway from this is that this method is suitable for relatively small matrices. When we start to get up into the 100 by 100 size, we're going to start to see a slowdown, not a huge slowdown, right? But if we're trying to do any kind of real-time operation, for example, we're really going to be getting too big for this algorithm to be effective. So the takeaway from this is that we're going to have to talk about some other methods, right? The upside to this algorithm is that it's relatively straightforward to implement. It's easy to implement, easy to maintain, just generally easier to work with. But again, it does have that size limitation. So before we move on, talking about other algorithms, we do have one more thing I want to talk about with respect to this particular method. It's going to impact some of the other methods as well. We have the potential to run into some calculation issues here where we hit those weird cases that we talked about back at the very beginning of the class, where because of the limitations of computer arithmetic, it's possible that we're going to run into some situations where, because of the way the numbers get rounded, we end up getting some really wildly off answers. And there are some things we can do to prevent that. They're called pivoting strategies, and that's what we're going to talk about in the next lecture.